I've looked at ways to evaluate limits graphically and on a calculator. Now I want to look at how to evaluate limits algebraically. And to do that, we're going to use the things called the limit laws. And there's going to be a few assumptions. First, we're going to suppose that A and C are constants. So you'll see those show up in the limit laws. Also, suppose that n is a positive integer. The limit as x approaches a of f of x is going to be assumed to exist. And similarly with the limit as x approaches a of g of x. Now all of these limit laws I'm going to write as two-sided limits, but keep in mind that all of them apply for one-sided limits as well. Now I'm not going to prove any of the limit laws, I'm just going to state them and then give a quick example. To prove them is a little more difficult, so for now just try to understand what they're saying. The first law, law number 1, is that the limit as x approaches a of a constant is just that constant. And then this one makes intuitive sense. If we think of f of x equals 1, then this is saying that the limit as x approaches, let's say 2 of 1 is just 1. And instead of as x approaches 2, I could have also said as x approaches 3 or 4 or 4.5 or whatever, the limit of 1 will just be 1. So here's a graph of f of x equals 1, and you can kind of see that as we approach 2 on the x-axis, there's 2 right there, it doesn't matter which direction we come from, we're always going to be at 1. And in fact, that works for any number right here. We can approach any number, and it will just be 1 right here. Law number 2 says that the limit as x approaches a of x to some power n equals a to the n. And as an example, let's look at f of x equals x squared. So this is saying that the limit as x approaches, we'll say 2 of x squared is just 2 squared, which is 4. Here's a graph of f of x equals x squared. And if we look at the graph, here is 2, so we are approaching 2 on the x-axis, and on the y-axis we should be approaching 4. So if we imagine going this way on the x-axis towards 2 on the graph, that would mean we'd be going up here, and on the y-axis that would mean we'd be going up here, and does appear to be approaching 4. And you can see the same thing from the other direction. We would be heading this direction here towards 2, and on the y-axis heading this direction, and we would be approaching 4. So this makes intuitive sense as well. Okay, law number 3. The limit as x approaches a of f of x and then either plus or minus g of x equals the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x. And keep in mind that we assumed that each of these individual limits right here, the limit of f of x and the limit of g of x, these two limits were each assumed to exist. If one of them or both of them do not exist, then this law does not hold. So this law only holds when f and g, the limits of those, exist. As an example, let's choose f of x to be x squared and g of x to be x. So this would be saying that the limit as x approaches, and again we'll say 2, of x squared plus x should equal the limit as x approaches 2 of x squared plus the limit as x approaches 2 of x. And that equals 2 squared plus 2, which is 4 plus 2, which is 6. And again, remember I said it only works if these limits of f and g exist. Now normally when we do a computation like this, we don't know maybe offhand if these individual limits do exist, but we go ahead and try it out and see. And if we run into problems, then we know we couldn't have done this splitting up here, this using law number 3 to begin with. If we were to graph the function x squared plus x, then this would be saying that as we approach 2 on the x-axis, we should be approaching 6 on the y-axis. And that does appear to be the case. As I get closer and closer to 2 on the x-axis, on the graph, we'd be moving up in this direction, and on the y-axis, we'd be moving this direction, and we would be approaching 6. And you see a similar thing when we approach from the other direction. It also does appear to be approaching 6. Next we have law number 4, and that's the law that says the limit as x approaches a of a constant, c times f of x, equals the constant times the limit as x approaches a of f of x. In other words, you can pull that constant outside the limit. As an example, let's choose f of x to be x squared, and we'll choose the constant to be 1/2. So this says that the limit as x approaches 2 of 1/2 x squared equals, well, I can pull that 1/2 outside and make it 1/2 times the limit as x approaches 2 of x squared, which is 1/2 times 2 squared, which is 1/2 times 4, which is 2. Here is a graph of x squared, and actually this is 1/2 x squared. And so we see that as we approach 2 on the x-axis, we approach 2 on the y-axis. And so again, you can check this graphically. Imagine getting closer and closer to 2 on the x-axis. You'll see we get closer and closer to 2 on the y-axis from either direction. So this one makes sense. Remember that this is not a proof. I'm just giving an example so that you get a feel for the limit law. Next up, we have law number 5. Law number 5 says that the limit as x approaches a of f of x times g of x equals the limit as x approaches a of f of x times the limit as x approaches a of g of x. And remember, these individual limits have to exist. This limit as x approaches a of f of x and this limit as x approaches a of g of x in order for this law to hold. For an example, let's choose f of x to be x plus 2 and g of x to be x squared minus 3, and you see the computation here. This time we're going to let x approach 1. And so the limit of these two things multiplied together, x plus 2 times x squared minus 3, should equal the limit as x approaches 1 of x plus 2 times the limit as x approaches 1 of x squared minus 3. And each of these individual limits do exist. So we get 1 plus 2 and 1 squared minus 3, which ends up being 3 times negative 2, which is negative 6. And remember, when I break it down like this, after I've used this first step here, this is using law 5 to break it apart. Then when I'm actually computing these individual limits, I'm using some of the earlier laws in order to go ahead and get the final answer here of negative 6. So the limit law number 5 happens right in the beginning, right here. As the graph here shows us, we have a graph of x plus 2 times x squared minus 3, and we're looking at x approaching 1, and so here is the 1 right here that we're approaching, and on the y-axis we approach negative 6. Okay, we have 2 more laws to go. This is law number 6. The limit as x approaches a of f of x divided by g of x equals the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. And we also have to specify that the limit as x approaches a of g of x is not equal to 0 because we don't want to be dividing by 0 here. For an example, let's let f of x equal x plus 2 and g of x equal x minus 1. And so the computation would look something like this. If we let x approach 4, for example, then the limit of x plus 2 over x minus 1 equals the limit as x approaches 4 of x plus 2 divided by the limit as x approaches 4 of x minus 1. And then I can use the earlier limit laws to break those down, and I get 4 plus 2 over 4 minus 1, which is 6 over 3, which is 2. And so the limit law that I'm using here, law 6, happens right here where I break it apart. And keep in mind that in order for this law to hold, both of these individual limits have to exist. Here's a graph of x plus 2 divided by x minus 1, has an asymptote at 1. And in this case, though, we're not concerned about what's happening near 1. We want to know as x approaches 4 what happens, and we see that indeed it does approach 2 on the y-axis. Okay, here's the last law. This is law number 7, and this says that the limit as x approaches a of the nth root of f of x equals the nth root of the limit as x approaches a of f of x. In other words, you can bring the limit inside the root. And remember that if n is even, then we need to have the limit as x approaches a of f of x being greater than 0, because we don't want to do square roots of negative numbers here. We're only dealing with real numbers here. As an example, choose f of x equaling x plus 3. And so a computation example here is x approaches 1 of the square root of x plus 3. That would equal the square root of the limit as x approaches 1 of x plus 3. And that's a limit that I can do using the earlier limit laws. So that would be the square root of 1 plus 3, which is the square root of 4, which is 2. Here's a graph of the square root of x plus 3. And we can see that as x approaches 1, so here's 1 on the x-axis, that it looks like we do indeed approach 2 on the y-axis. So to summarize, Here are each of the 7 laws that we've seen so far. These are the limit laws. Keep in mind a couple things. What I just shown you in this video here is not a proof. None of these things were proofs. They were just examples and just a demonstration of the limits graphically and with the computation so that you can see intuitively that they make sense. Also, keep in mind, this is very important, that in order to use these laws, the individual limits, the limit as x approaches a of f of x and the limit as x approaches a of g of x, both of those limits have to exist. Otherwise, these laws do not hold.